Alright, so let's talk about calc intersect and calc zero. So if you recall, we're trying to solve this. Let me just go back to the question. We're trying to solve this. Okay. Now, I don't want to pretend like this isn't an easy question to solve just from first principles. It is. All you would have to do is move 12.1 to the other side and then divide by negative 19.4, and you'd have your answer. So the point in learning this is not that it's a better method for solving a linear function. The point really is that when we get to more complicated functions later, that you will want to use this method I'm about to show you, and it will be easier. Okay, for linear functions, yeah, probably just solving it by hand is the easiest way, but nevertheless, we're going to do the calculator method now. So here's the idea. Actually, let me just draw a picture to show you kind of what we're getting at. We're trying to find when this function, which is a decreasing linear function about the distance, my distance from home and out in miles as I travel home. So we start off, and I think it was 12.1, and then we want to know basically what that value is there, right? Sorry. So this is an intersection of sorts. This is an intersection, but it's intersecting with the x-axis, right? So and actually it's not actually the x-axis in this case, it's the t-axis, so let's just say it's the horizontal axis. And what that is we're finding the zero of the function. Finding the zero. And when I say finding the zero, I mean we're finding where the function is zero. So it's not that the input is zero, it's the output is zero. And there's a calculator procedure for this, and it's called calc zero. Calc zero. And it's very similar to calc intersect. It's just basically it's like calc intersect applied to a particular kind of intersection, which would be an intersection with the horizontal axis. And here's the way it works. Let's pull up the calculator. Okay, let's clear all this stuff. Now I don't actually have the function entered, so I better do that. What is the function? I've forgotten. Negative 19.4x plus 12.1. Okay. So that's negative 19.4x plus 12.1. Okay. That's my function. Let's look at a reasonable window. Let's try we can leave it at 0 to 30, but let's make sure that we have a decent zoom fit, so let's try that. Oh, that's not very good actually. That's too big. You see here is the origin. Let's change it to 0 to 10. And then we'll try zoom fit again. This is better, but actually I could go quite a bit smaller than that. That's 1 right there. So let's try one more iteration of this. Let's just go to 0 to 2. There we go. I like that picture a lot better. And I can see this intersection with the x-axis. Now, I want to use calc 0, so I'm going to go to second, trace, and instead of calc intersect, we're going to go to 0, which is right here. And it's going to ask you slightly different questions. So notice that the first question says left bound. What that means is you want to move your cursor and you want to think horizontally here. So is my cursor on the left of the 0? Well, the 0 is right here. So left of the 0 is going to be over here. Right of the 0 is going to be over here. So left bound is, I'm not at the left bound, so I actually need to move this over. So I'm going to just use my cursor, my right entry, and just follow along the curve until I'm on the right of it. Now, whether or not you're above or below it, that's not important. What's important is that you're horizontally to the left of it. I think I said right, but I meant to say left. Then you hit enter, and then you see it put this little triangle right there. Now I want to go to the right bound, so again I'm going to move to the right, and I'm clearly on the right of it now. And now it wants me to guess the intersection, and I think it's about right there, so I'll move my cursor until I'm on top of my guess, and that looks good. Hit enter, and it will calculate the value for me. It's 0.623. That's 0.623 of an hour. Okay, now that's what's going on here. And so 0.62 is approximately 0.62 of an hour. I will be at home, right? Okay, so we just learned about this Calc Zero method, and we talked a little bit about zeros, but just to sum that up, a function's horizontal intercepts are called its zeros. So, for example, let's look at this. That's a 0. That's a 0. This is not a 0 right here. Okay? So this function that I've drawn up here has 2 zeros. Now, Calc intersect can be used to find a function's zeros. That's true. But Calc Zero is slightly more convenient. I didn't actually talk about using Calc intersect. If I was going to use Calc intersect to find the 0, I'll show you what I would do. Just very briefly, I would actually type in 0 as my function here, as my second function, and then I would use Calc intersect in the same way that I did in other examples. So you'd graph it and then go to second trace intersect. But I would just use Calc Zero if I'm actually finding a 0. All right, very good. So there are your answers. Here's another set of questions about the same problem, the same late afternoon commute model. And all of these questions are about finding average rate of change. Now remember, this is a linear function, and so your average rate of change, we know the answer to this already, or at least we should. The answer is going to be negative 19.4 because that's the slope of the function. So we expect to get that value for each one of these. Now to actually do this, we would be calculating, just for the first one for example, that would be y1 of 0.3 minus y1 of 0.1. And that would all be in parentheses, and then we would divide that by parentheses 0.3 minus 0.1. And similarly for the next two, except we'll be using these new values. And for each one of these, you will get negative 19.4. Now, why? Well, because it's a line, and the average rate of change of a line is constant, and the slope of a line is its constant rate of change. So you really don't even have to perform these computations if you are looking at a line. You just have to be aware of what its slope is, and then you know the average rates of change over any interval. All right, you ready for a new example? I am. Let's take a look at this. It's another population model. We are told that we have a population of 375,000 on July 1st, 2000, and is growing by 9.25 thousand people per year. So assume this trend continues. And question A, find a model for the city's population in thousands as a function of the number of years after July 1st, 2000. So this is a new question because in this one we are not given the model. We actually have to develop the model, which is a little bit more realistic. Now we're still told quite a bit about the model, but it's not explicitly given to us. Now I know that its initial population is this. Okay. And then I'm also given this number that says it's growing by 9.25 thousand people each year. So what is that? So this means every year we gain 9.25 thousand every year, that same amount. So that, if I think about it, if I start off at say 375, I go 1 year over 9.25 up, 1 year over 9.25 up, 1 year over 9.25 up, and then connecting the dots there, you've got a line. So this is a linear function. So it's linear, constant rate of change. And what is the form of the linear function that we're going to work with? Well, it's AT plus B. So A is the slope, and now since we are growing, that's going to be a positive slope in thousands. And then remember that B, that's your y-intercept, that's your initial value, so that's going to be 375. And I'm getting these numbers just from the problem. Now, I did something else here. I reset the clock because the problem told me to. So that's resetting the clock. That's elapsed time. And so I reset the clock here, so T0 represents the initial time, and that's going to be my population model. Okay. And now the next two questions are just about using that model. So what was the population on July 1st, 2010? That's 10 years after the initial. Well, let's plug it in and evaluate. This is a type 1 question. So 9.25x plus 375 is my model. Let me just make sure I'm getting the right values. Yes, I am. Okay. And then I want to know in 2010 the value of the function. So that's a vars y vars question. And 2010 is 10 years after 2000, so we have 10 years elapsed time. And so there's my output, 467,500 people. Question C, use the model to predict the year when the population will reach 600,000. This is actually asking me for the calendar year, but we're going to find first the elapsed time. And this is a type 2 question. So we're going to use calc intersect here. So I'll go to y equals, and I'll put 600 here. Now I want to know how many years it takes me to get to that, and we could, let's actually take a look at the table and see if we can identify this. Oh yeah, there it is right there. So between 20 and 25. So that gives you a good window. So we can go ahead and let's go 20 to 30. And then we'll do zoom fit. And we should see a decent intersection. And then with that intersection, we'll use calc intersect. So there's our nice picture. We go to second trace. Calc intersect is number 5. First curve, yes. Second curve, yes. And my guess, that's about right. So enter 3 times and we come out with 24.324. Now, very quickly, that's 24.324 years after July 1st, 2010. So, take a look at our solution here. We'll finish this up in the next video.